Problem number 1 on chapter 9 demo. The data shown below represents the age in weeks at which babies first began to crawl. Based on a survey of 12 mothers, complete the following. Draw a normal probability plot to determine if it was reasonable to conclude the data came from a population that was normally distributed. There were 12 mothers who were surveyed, or 12 measurements on the ages at which babies first crawled for 12 babies. Because the sample size is less than 30, and it is quantitative data because it's a measurement, we first have to kind of verify the conditions for it. So for quantitative data, you either have to have a sample size greater than 30, or it came from a normal population to begin with, or roughly normal. So we're going to make a QQ plot. So let's open up in StatCrunch. They're saying to draw a normal probability plot, but on StatCrunch, it's labeled as the QQ plot. So they gave us the plot there, but we had the, they gave us the table of critical correlation coefficients to compare it against to see if we have a stronger relationship than what's required from the table. So we go to graph QQ plot, variable 1. Let's add the correlation coefficient, compute. So let's see what this is. So as looks like it's a pretty strong relationship. Now this one is reversed, so be careful, because here, remember I had mentioned that before in one of the previous videos. Here they have the normal values, which are the like standard deviation 0, 1. And look on the vertical axis, it's 25, 30, 35, 40. And all of these have the Z value on the vertical axis and the age in weeks on the horizontal axis. So to flip this, we're going to go to Options, Edit. And this normal quartiles on the Y-axis, we're going to select that. So now it looks like one of our diagrams. So these two, it's either choice A or D in terms of choosing the correct diagram, first of all. These look pretty similar here. So you have to be really careful. I'm trying to see if there's a difference in one of the measurements. Maybe this last one here. So these are, so just kind of match whatever it looks like for you. So I'm looking at the pattern of the first 3. This is kind of steep. And then this is 2 here, and then it kind of tapers off. So I have 2 here that kind of taper off as well. So just with the first 3 dots, it's more similar to D. But those two are very close. So you have to just be careful, extra careful. And now we're going to say, since the correlation between the expected Z-scores and the observed data, which in my case is 0.991. If you forgot to, if it's nothing is showing up there, go back to Edit, Options, Edit, and make sure you select the correlation statistic there. And now we want to compare that and see if it's higher than what's on the table. If we met the requirement that it has to be greater than what the cutoff is for us to determine that there is a relationship. So we have to look for our sample size, which is 12. Here it is. So it's the critical value. I'm going to write it over here. Critical value is 0.928. So my correlation coefficient has to be greater than that for us to be able to do analysis in this section. Mine's 0.991, so it is higher than the critical value. So since the correlation coefficient exceeds the critical value, the cutoff, which was at 0.928, then it is reasonable to conclude that it's roughly normal, that this data is roughly normal. You could also get a visual. Sometimes we'll choose the QQ plot. Sometimes we'll pair that up with the box plot, because a lot of times the box plot will identify any outliers. You don't have to do this here because they didn't request it, but just so you can see, it looks pretty symmetric here. But the important thing here is just to say that there's no outliers, which there aren't. So those two graphs together kind of confirm that there is a correlation. It's set to round to 3 decimal places. I don't know if I was paying attention to that, but I did round it to 3 decimal places. That's usually the standard. And then it says draw the box plot. Okay, so I got ahead of myself here. So now let's do it. Graph, box plot. Click on the variable and draw it horizontally. Compute. And then mine starts like at a little bit over 25. So here's 25. This is 25. They all look like they're starting at the right place. But the shape for mine, my right-hand side is larger than the left. So it cannot be A. This looks close, but then this tail seems kind of short. I think the best one is this one. But I'm gonna hover here for the 5-number summary and see if it looks like, let's see if I pop this one out and see if they're hitting around the same places. So now that I popped it out, it definitely looks more, but this looks like at 41 or 42 and like 49. Cool. Sometimes I click that in it. So I said it was like 41 was the medium, okay. And like 49 is the Q3. Yeah, it looks like that's hitting at the, so I'm just being a little bit careful, seeing where these markers are hitting, make sure my graph matches, because they kind of look similar. So you might think it's this one, they're kind of, or this one, but just scaled differently. So just be a, if you choose the wrong one, just kind of maybe see those measurements. Does the box plot suggest that there are outliers? No, there's no little blue points here. So the two before, the two no's. There are no points that are greater than the 3rd quartile and less than the 1st quartile. Well, there are points that are bigger than 3rd quartile, because here's the 3rd quartile. So there's points that are bigger, and here's the 1st quartile. There are points that are smaller. So that's not it. See, there are no points outside the fences, which are the 1.5 IQR above and beyond the boundary. So that's how we measure it. That's how we measure if something qualifies to be an outlier. It has to be more than 1.5, which is 1.5 of these lengths. The IQR is the length. So if I go one box of that length and a half, whatever that cutoff is over here, that would be, anything below that is an outlier. And the same thing on the other side. That was from a previous chapter. Construct and interpret a 95% confidence interval for the mean age that which babies first crawl. So we could come, let me erase this because it's under the data that, I should have put it over here. Let me, that I'm going to be analyzing. We could find the average of age here, but that's the average for these 12 babies. Does that represent the average of all babies? No, but using that average, if we're doing things correctly, we can use it to kind of estimate what the true, like a little interval or window in which the true average age would be between. So to do that, we're going to go to stat. And you have 3 choices for confidence interval, depending on which test you're doing. If you're doing a test on quantitative data where you summarize it with means, you're going to do t-stats. If you do a analysis on categorical data, which are measured in proportions, then you do proportion stats. And if you do a analysis on standard deviation of quantitative data, because that goes with means, then you would do what's called variance stats. So we're doing means, so we're going to do t-stats. Those are the only 3 we use. Z-stats is like for a perfectly normal bell-shaped distribution, which we rarely have those, so we're not going to be using that. Okay, we have one sample. Later in a later chapter, we're going to deal with two samples, like for your project males versus females, or pair data like a before and after, or like a wife and a husband that you're doing analysis with. But for now, this chapter, just one sample. They gave us the actual original data, not they didn't summarize it. So let's go with data. Choose our variable here. And future chapters, we're going to be doing hypothesis testing, but this chapter, we're going to do confidence interval. So let's select that. You can also get a visual for the length of the confidence interval. So I'll do that this time around just so you can see what that is saying. Okay, so for these 12 babies, the average weeks that it took them to first crawl was 41.5. So about 10 months old, give or take. Is that 10 months the average for all babies? No, but we're confident that it's between this lower limit and this upper limit. So here's a little window based on that measurement from the sample that tells us, okay, maybe it's not 41.5 weeks for all babies, but we're 95% confident that it's somewhere between 35 and 47.6, whatever. So we know the truth for the entire population is in here. Can we guarantee it 100%? No, but we're pretty confident. Okay, so that's to one decimal place. So we're doing a 95% confidence. This says a 95% probability. No, this one says 95% confidence. So always choose the one that says confidence. They try to throw you off with that probability statement, which is incorrect. So we're 95% confident that the mean age at which a baby first crawls for the entire population is between, and then round your answers to the nearest 10. So for mine, it's 35.5 and 47.7. Now, what does it mean to be 95% confident? It doesn't have anything to do with this particular example. I mean, for any sampling that you're going to do where you're 95% confident means that if you were to repeat this 100 times, 95 times out of every 100 samples of size 12, you would get these little intervals that would capture the true population measurement, in this case of the age that babies first crawl. And 5 times out of 100, you would get some data that actually misses the truth. It doesn't capture the population true mean. So it's kind of like the risk of being wrong. So if you were to repeat this 100 times, you would be wrong 5 times. You wouldn't capture the true measurement for the population, and 95 times you'd get intervals that would capture the true population measurement. And that's for any sampling. It could be proportions, it could be variance, it could be means. So the more confident you have, the bigger this window has to be so that you guarantee that you're capturing the truth. And it depends on the type of research. If it's something very like strict where you have to be, you want accurate, really accurate results, then maybe increase the confidence interval level so that you know you're guaranteeing that you're going to be correct. So once in a while we can be wrong, is what we're saying, but not that often. So it doesn't happen too often. So we're pretty confident that we have good numbers there. Here's problem number 2. It seems similar. The following data represent the age in weeks at which babies first crawl, again, based on a survey of 12 mothers. So let me close this one because it's a different set of information. It's not the same thing. So let's open up this in StatCrunch. The data is normally distributed. So now they're saying that it's roughly normal. We don't have to do the check ourselves or verification. And they told us they didn't tell us what the average was for these 12 babies, but they're telling us that the S, which is the symbol for the standard deviation, is 10.46 weeks. So that's how much these babies typically deviate from the center, whatever the mean is here. The symbol S is the symbol for standard deviation, but for a sample, not for the population. Construct and interpret now a 99% confidence interval. We want to be more confident that we've actually captured the true mean for the population. So construct, well, actually, that I didn't read what it says next. Construct and interpret a 99% confidence interval for the population standard deviation. So not for the mean. So we want to say, okay, this is the standard deviation for these 12 babies. That's what it typically deviated by from the center, whatever the center was, maybe 40 weeks, maybe not. We want to know, did we capture the true standard deviation for all babies? So that's what we want to say. Okay, maybe it's not 10 weeks that they typically deviate for all babies, but we want to come up with an interval, some window that we can say, oh, in this interval, the true standard deviation for all babies is somewhere in between these two numbers. So stat. So the last one we went to is t-stats because we were doing means. Variance stats and is standard deviation squared. So the way that it's programmed in most technology is that they put in formulas for variance, and then we have to adjust for standard deviation. Okay, so we only have one sample. Again, we have the data. Choose our variable. Select confidence interval, but now we want to be more confident, so we want to increase this. And the last time I said, let's look at what the confidence interval plot looks like, and I forgot to mention that, so let me do that here. Compute, and let me do that first before I forget. So this one is between 44 and 462. So let me go here. So this is where our standard deviation sample variance is. This is variance, it's not standard deviation. So the issue here is that this gives us the standard deviation squared because of the way it's programmed. So if they want the standard deviation, we have to take the square root of that because this is the squared version. But even for this interval, because let me look at it again. The square root of like 100 is 10. The square root of 400 is 20. So maybe a little bit less than 10, a little bit greater than 20 is where the standard deviation should fall in between. So maybe it's, if this is like 80, then, you know, it may be like 9 or 8 is the lower end in terms of standard deviation. But that's the little window that they come up with, that the truth must lie in somewhere in between here in terms of the variance. And if we take the square root, then the truth must lie somewhere in here. In terms of the standard deviation. So that's what we have to be careful with, that the StatCrunch gives us the these standard deviations squared because of the way it's programmed. If it says variance over here, then we don't have to adjust it. But since it's standard deviation, then we're going to have to take that into account. So the first number, I'm going to take the lower bound here is, I guess I would want to do the whole thing so I don't have rounding error. I mean, that's already rounded as it is, but since that's the squared version, I want to do the opposite. So square root, bring it back down. So that's, let me put it right here. That's 6.7050. We're only going to do one decimal place, so I don't need to know that many. And then I'll take the upper limit, the upper bound, which is 462.08764 for mine. Take the square root. So my upper limit is 21.496. Now remember, the standard deviation for these 12 babies was 10. So maybe it's not 10 for all babies, but somewhere between 6 and 21. This one doesn't make sense because if yours is 10 and this one's saying it's somewhere between 44 and 462, 10's not even in there. 10 should be in there because this window is based on using that 10 to begin with to come up with the window that's going to guarantee that you've got the actual population measurement. So for all babies, then they would typically deviate from the center, the mean, either as low as 6 weeks up to 21 weeks is that variation. So somewhere in there is the true standard deviation for the entire population of babies. Okay, so now I have to select the correct one. So remember, This one says construct a 99% confidence interval. And this one says 99% probability. This one says probability, and this one says confidence. So it's between these two. So if we repeated samples are taken 99% of them. No, that's on the sample. This has not, this confidence interval has nothing to do with the actual sample. It has to do with if you were to repeat this, what's the risk of being wrong? So this is already tying it with the actual experiment at hand, which they're not connected. So, and in fact, this is the only one that said 99% confidence. So that's another kind of clue that that's the one that's stating it correct. So in this case, 99% confidence means that if you were to repeat this sampling 100 times and come up with 100 little intervals or windows that are telling us that the truth is in there, 99 times we would get little windows that actually contain the true population mean standard deviation, and one time out of every 100 samples, we would be wrong. We wouldn't get an interval that captures the true standard deviation for the population of babies first crawling. So again, this just measures the risk of being wrong, or the kind of chance of getting it right as well, of capturing the truth. But that's in general for any experiment. It has nothing to do with this particular experiment. That's in general. Okay, so 1 decimal place. Okay, so let me, it's a new data set, so let me close this one. Let's open this up in StatCrunch. A jar of peanuts is supposed to have 20 ounces of peanuts. The filling machine inevitably experiences fluctuations in filling. So a quality control manager randomly selects 12 jars of peanuts from the storage facility and measures their contents. Okay. Verify that the data is normally distributed by constructing a normal probability plot. So we're just going to make sure that the conditions are met for us to do an analysis because the sample is less than 30. So let's, a normal probability plot is called a QQ plot in StatCrunch. Choose a variable, correlation coefficient. I'm not going to do this one because this one says to put the Z values, the normal quantiles, on the y-axis, and this one has the Z values on the x-axis. Well, there's 2 of them. Okay, let's see if 2 of them have the Z values here. Well, actually, just 1 of them. All the other 3 have the Z values there. So if ours doesn't look like one of the options, then I'll flip it. Okay, so this one has the Z values here. It's like well, this one kind of matches it. If I flipped it, I don't know if I would get any of these other pictures, just out of curiosity. Let me try that and see if. So this one starts at 19 and then it kind of jumps up. So that one looks straight. Perhaps this one kind of looks similar as well. But this one starts at negative 1.75. And this one is, that's 0, that's negative 1, and that would be negative 2. So yeah, that could potentially be it as well. I'm looking at the rest of the points. So this last one's about 20.6, 20.5 at a height of a little bit below 1.75. So I think this one's too low. This looks like it's like less than 1.5, and this one looks like it's 1.75. So yeah, then it must be this first one. Nope, that's incorrect. So then it's this one. I'd have to pop it out. Maybe if once I pop it out, it's going to be a little bit more accurate. So this one's right below 20.6 and right below, oh, it's below 1.75. It's kind of hard to read there, but it was between those two. I can analyze this and see which of these dots was off. So one of these might have been off in my original diagram. Is the data normally distributed? So the correlation coefficient here is 0.981. And let's look at the table. Oh, they don't give us the table. See, this is one of those examples where it's not given, but 0.981 is pretty high. I would say yes. I had it in the previous example when I wrote it, but if you want to verify it with the table, you can look on the homepage of Canvas, and I have the table there, and you can pull it up. But we're not, most likely it's going to be, it meets the requirements. Otherwise, we're not going to be able to do like a confidence interval. So we could just assume it's going to be yes without looking at the table, but it will be. It will meet the conditions. Okay, determine the sample standard deviation. Okay, so that we will get from the summary stats. Column 1, and it's in here, so I'm not going to select it. I'll just do everything. So this one, the average is 19.9, so about 20 weeks is the average or mean crawling age for this group of 12 babies. Oh no, this was not the baby problem, it was the peanut butter jars, right? My mind is still on the previous example. So the mean is 19.9 ounces. Yeah, they were measured in ounces. So it's about 19.9 ounces is the average. It's a little bit lower than what the company is claiming, which is 20. So they are a little bit below. So they might want to recalibrate their machinery to guarantee the 20. But they're asking here for this group, how much did it typically deviate from that 19.9? And the standard deviation from these 12 jars is about 0.3 of an ounce. They want it to 3 decimal places. So it contained about 19.9 ounces, give or take about 0.34 ounces. So if you do the window, the 20 will be in there for just like the mean weights. Construct a 99% confidence interval for the population standard deviation. So be careful, because in this chapter, you're coming up with these confidence intervals where you're kind of guaranteeing that the true population measurement lies within, but we're doing it on different types of measurements depending on if you're dealing with quantitative or qualitative data. So here we have 3 choices. The t-stats if you want the confidence interval for means, proportion stats if you want the confidence intervals for something that was in proportions, which was for categorical data, and then variance stats if you're coming up with confidence intervals for standard deviation or even variance. So in this one, they're doing standard deviation. So that's the one we're going with. One sample, we have the data. Let's choose our variable, choose the confidence. Now, always be careful. We might have to modify the level. So this one says 99. So let's go ahead and select that, make it 99. Okay, so here's the variance. It's not standard deviation. So I have to take those 2 numbers and I have to take the square root. So my lower limit is 0.04. Just kind of type in all those numbers so that you don't have any rounding error. And we're going to round it to 3 decimal places. So let me put it here for now. So 0.221. And then do the same thing for the upper limit or the upper bound. Okay, once you do that, and if you're, behind, just pause the video for a minute until you figure out what your numbers are. If repeated samples are taken, 99% of them, see, that's relating it to the sampling, which the level of confidence has nothing to do with the actual experiment, because this 99% confidence interval is true for any experiment. There's a 99% chance 99% confidence or 99% probability. So here it said confidence. See how it's worded in the problem? You should match it with what we want. And then put your values in. So the sample resulted in a standard deviation of 0.344. Is that the true for all jars of peanut butter in the company? No, but the manager could be 99% confident, which means almost 100% sure that the true variation is somewhere between 0.221 and 0.708, that it can vary as low as this amount or as high as this amount. So the true standard deviation for all the jars would be somewhere in between there. So he wants it to, the quality control manager wants the machine to have a population standard deviation below 0.20 ounces. So that's the goal. So does this confidence interval validate this desire? Well, if 0.20 could be one of the possible standard deviations in the window, then yeah. But if it's not in there, then no. So let's see. Mine starts at 0.221. And 20 is below that. So this 0.20 is not in this little window here, this little interval. So he's not meeting his goal because if the truth is somewhere in between here, it doesn't capture 0.20. So he wants to lower the standard deviation a little bit more. So he might have to recalibrate the machine because it still looks like it's still too high for what the goal is. So does this confidence interval validate this desire? No, because the lower bound is less than 0.20? No, because the lower bound is higher than 0.20. Yeah, this lower bound is higher than 0.20, not below. So the wording, just read carefully. A simple random sample of size 200 individuals who are currently employed is asked if they work at home at least once per week. Of the 200 employees surveyed, 38 said they did work at home at least once per week. Construct a 99% confidence interval for the population proportion of employees who work at least once per week at home. Okay, so here's the confidence interval. We're doing it now for a proportion, which means this was categorical or qualitative data, a yes or no question. Did you work at least once a week? Yes or no? And then we can see what percent of the sample said yes or no. If you want, you can open a new window or you can just use this one. You don't have to open a new window. Let's see if it gives us the choice here before I close it. Yeah, it does so. I'll go ahead and open a new window just so it doesn't cause confusion. You're seeing other numbers there and you're thinking we're using them. But if you're okay with using the same window, it's fine. Okay, so if we're going to do a confidence interval, that's stat. And this time it's proportions because it's a they stated it. One sample. A little bit. Excuse me. Adjusting my windows here so we can see the the output. Make this a little bit bigger. Stat proportion stats, one sample with, doesn't give us raw data this time, it gave us the summary. So they kind of counted it for us. So in how many people said yes out of the total observations? The successes were 38. They were counting people that answered yes. Number of observations is the number of people or samples taken, in this case 200. We're going to want a confidence interval 99. So we have to change this. If it's not, it's on default, it's 95. We'll do the confidence interval plot. Okay, so the sample proportion is the 38 divided by 200. For this one sample, 19% answered that yes, they worked at least once per week. Is that the truth for the entire population of people that work? No, but we could come up with a window where we believe the truth lies within. So this value here is the sample of 0.19. And based on that sample, we can come up with a little window, say, okay, maybe that's not the truth for the population. It could be, but most likely not. But we can not guarantee 100%, but we can be confident that it's somewhere between these two numbers here. So 0.12 and 0.26. So somewhere between 12 and 26% of the population works at least 1 day a week. So let's go back to the first window here. So the lower bound, round to 3 decimals. I'm looking at the wrong place here. Let me make this better. This point. And then you enter the upper bound. A random sample of size 25 is drawn from a population that's normally distributed. So they're telling us that since this symbol here is for means, then we would need to be at least 30 or larger. So they're telling us, okay, this is less than 30, but we've checked it. It comes from a population that's normally distributed, so we don't have to meet the requirement of it being large enough. The sample mean for this group of 25 happens to be 52. And the standard deviation of the sample is 20. And now construct a 95% confidence about the population mean. So here the key word is that you're doing it on a mean. So let's say this was the age at the average age at which people first get a gray hair, let's say, give or take 20 years. So for the sample, so they asked 25 people at what age, how old were you when you got your first gray hair? And the average age turned out to be 52, but you know, the typical deviation from that center was 20. So if I wanted a window of typical values for these 50 people, it would be, I mean, for these 25 people, it would be 52, give or take 20. So between 32 and 72 would be the typical ages when people first get a gray hair. Is that the truth for everybody, 52 years old? No, but we can come up with a window where we believe the true population age does lie within. So stats, T-stats, because that's the one for means, one sample with the summary. They didn't give us the raw data this time. So what was the average for these for this group, 52 years old? What did it deviate by 20 years? How large was your sample size? 25. So here it is in words, but over here it's symbolically. So it's important to learn the symbolic notation, what all these symbols represent, because we have a symbol for mean for the population, but this symbol is reserved for samples. And we have a symbol for standard deviation for the population, but this one, S, is reserved for a sample. So a lot of symbolic notation. We have to be careful with that. Okay, this one's 95% confident, so I'm going to keep it there, but if yours is different, then change it. Compute 2 decimal places. So in context of what I was talking about, is the true age when average age when people first get a gray hair 52 for the entire population? No, most likely not, because this was just based on a sample of 25 people. But we're 95% confident, which means we're pretty confident that the true average age when people first get a gray hair is somewhere between 44 years old and 60 years old, that the truth for the entire population is in that little window based on this one sample, that the truth will lie in between there. find the critical values. Okay, so critical values are a little bit different. It's that cutoff, those distances from the center, like those standard deviations, that if you go beyond, then you have unusual results. So we could do it for means, we could do it for proportions, or we can do it for standard deviation. So like for a perfectly normal curve, to be unusual, you'd have to be more than 2 standard deviations on both sides, but it changes for sample size, it changes for whether it's in proportions or like this little chi-square symbol. But all critical values, you get them from the calculator. So stat calculators. And we've used binomial in the past. Normal will be for proportions. T will be for means. And the one for, there's no standard deviation or variance here. And it ends up being this thing called chi-square. So these are used for when we're doing tests on standard deviations or variances. So we want to be 98% confident. So we want to, these confidence levels, when we do them here, since there's 2 values, they're always the between, because we want to capture the middle 98%. So I'm going to change this to 0.98. And the x's here, I mean, this is a chi-squared, it's the symbol for chi-square. It's not like x squared, it's chi-square. It's still the number of standard deviations, like the z value or the x value here. It's on the horizontal axis. So the one that says 1 minus alpha over 2 is the one on the left, and then the one that says alpha over 2 is the one on the right. So it's what we're looking at is the cutoffs though. Like, so if we were doing a sample and we got something in this region, it would be unusual results. Or if we got something over here, it's considered unusual results. So this allows us to see what the cutoffs are. Wherever the center is here, here's the peak. So wherever the center is here, then this would be considered so far away from what we would expect to be in if nothing was going on, or like the typical results, that to be unusual. So 3 decimal places. We use this idea actually in hypothesis testing, which is the next chapter. I'm seeing if I forgot to do my degrees of freedom. Oh, here, I forgot to talk about it because I got that wrong. This degree of freedom is something new that's showing up that we didn't have before. Degrees of freedom are, out of a sample size of 10, you always subtract 1 from it. So you could either put it here or you could just put 9. Let me put my 0.98 again. So put 9, or it's always less than, if the formula is n minus 1 for degrees of freedom. That's why I had it wrong. It's kind of a tricky concept to explain, but it's kind of like once you decide what the first person is, or the first in the formula, sort of like if you have 10 people who are going to sit in 10 different chairs, if the first person sits down, then you don't have 10 choices anymore. Now you have 9, and then that's what we're working with, but a lot more complicated than that. So let me enter now the correct values. Sometimes you were doing the stat crunching, you might forget one thing, and then especially like when you don't click on variable 1 and then it says, oh, error, you have to at least pick 1 variable. So sometimes there's a lot of things we have to change, and we can occasionally forget something, and that's where we kind of get the value wrong. So let me close this one because now we have a table that we're going to open up in StatCrunch. So let me get that ready. The following data represent the pH of rain. for a random sample of 12 rain dates for a particular region. It is a measurement, so we should have a sample size of greater than 30, or the data doesn't have any like significant outliers. It's roughly normal to begin with. A normal probability plot suggests that the data could have come from a population that's normally distributed. Okay, so they checked it for us. There's no outliers in this set here. So the box plot indicates no outliers. They probably did a check the critical value for a sample size of 12. Okay, so that means we can go ahead and do the analysis. The sample standard deviation is 0.315 units of acidity of pH. Construct and interpret a 90% confidence interval for the standard deviation. So here we go. 90% confidence interval for the standard deviation. So because it's either going to be means, proportions, or standard deviation. I don't know if they'll give us any that are variance. Sometimes they'll give us examples that deal with the actual variance. Okay, so here we want standard deviation, so that's going to be variance. We have one sample, and this time we have the actual original data. So we'll select our variable. We'll do a confidence interval. And for my problem, it's 90% confidence interval. For your problem, make sure you choose whatever your problem states. And because this has a little square on it and they want standard deviation, then remember this is the one we have to break back down to a standard deviation. And again, use all the numbers that are showing up on your calculator. So my lower limit, I'm going to enter here with no rounding. And we want 3 decimal places. So I'm going to put it over here for now. And then do the same thing for the upper limit. And now we want to choose the correct answer. 90% probability, no. This is 90% confidence. Oh, this one says 90% confidence. What does this one say? If you were to repeat the samples and 95, okay, this confidence has nothing to do with the samples. 90% of those samples, no, that's not what the confidence interval does. Confidence interval works for any sampling that you do. It's just telling us the likelihood that we can guarantee that we'll get the correct answer. But that's for all experiments, not just for this one. So it's a general idea for all, like the risk of getting it right, the risk of getting the wrong in terms of capturing the true population measurement. So it has nothing to do with this particular example. Okay, so we're 90% confident that the true standard deviation for all pH levels of rain is somewhere between these two values. The sample was 0.13. Notice that 0.13 is in here. So it could be as low as, the pH level could be as low as this one, 0.235, or as high as 0.488. The truth is somewhere in there. As to what it is, we don't know. We just come up with a little window that says, okay, it's somewhere in between here. Okay, so that was the last problem in chapter 9.